how Newton might interpret gravity was sufficient to permit us to fly from the Earth to the moon at any point. Get yourself lost in the ticking hands of time, contemplating whether how we might interpret it is simply the tip of the worldly chunk of ice on its head is. Disclosure isn't simply a hypothesis. A key could open the ways to the secrets of the universe, uncovering a universe more many-sided and moving than we had any point thought for even a second to envision. How does Brian Cox's new hypothesis challenge our customary comprehension of time, and what are the potential suggestions for our impression of reality? Go along with us on a captivating investigation through the archives of time itself as we dive into Brian Cox's as of late uncovered earth-shattering hypothesis on the concept of time in the huge universe around us. Secrets are pausing to be uncovered, and a portion of these secrets involve perplexing things about time and gravity, which are fundamental portions of our reality. Imagine a world where time acts unusually. Can all things considered dial back or accelerate? Additionally, the power that keeps us on the ground probably won't be what it seems to be. This is the domain of Albert Einstein's theory of relativity, where how we might interpret time and gravity goes off in an unexpected direction. Albert Einstein, a notable name, gave us a better approach for taking a gander at the universe. Through his theory of relativity, his work established the groundwork for understanding how time acts in either circumstances, particularly when going at incredibly high rates. It all started in the mid-20th century when Einstein proposed two earth-shattering speculations: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we might interpret reality. In basic terms, it lets us know that the laws of physics remain the same for all observers who aren't accelerating, no matter what they are movement. This hypothesis presents the possibility of relativistic effect, including the renowned thought that time can expand or dial back under certain circumstances. One captivating psychological study used to make sense of time dilation is the light clock. Imagine being inside a spaceship moving unbelievably fast. The current understanding of time and physics nearly at the speed of light. Inside the spaceship, there's a light beam skipping between two mirrors, opposite to the direction of movement as indicated by the laws of physics. The speed of light is constant for all observers, so the light beam must seem to go along a more drawn-out slanting way. The time it takes for the light beam to travel its way ought to be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the outside observer, it seems like it would take additional time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the fixed observer in the situation. Time acts in an unexpected way depending on your movement, getting at how things change when they move quickly. Known as relativistic effects isn't simply a hypothetical thought. Researchers use huge machines called particle accelerators, like the Large Hadron Collider, to make particles go really fast, nearly as fast as light. When things move this quickly, we need to contemplate time in an exceptional manner to make exact predictions and estimations. Albert Einstein concocted the special theory of relativity in 1905, and it changed how we see the universe, particularly when it comes to time and movement. This theory challenges what we could normally think. It says that the standard rules of physics are no different for everybody, regardless of whether they're not moving. This is different from our ordinary experience, where we might feel that if something is already moving and we add more speed, it gets quicker. However, Einstein's theory says there's a maximum speed that nothing can go faster than, and that is the speed of light in this perspective. Events that appear to occur simultaneously for us probably won't seem that way for people moving around nearly as fast as light. Another concept that comes from this exceptional perspective is length contraction. This means that if something is moving, it looks more limited in the direction it's moving when seen from a fixed spot. Then there's the renowned equation EMC caret 2, which demonstrates how energy and mass can change into one another. This is significant for understanding how small particles act while they're flying around super quickly, and also for things like what happens when atoms split. Nuclear reactions in this present reality. Special relativity isn't simply an abstract theory, it's something we use in regular advances like GPS. When GPS satellites send messages to your device, they're moving, and because of this movement, time acts a little differently for them. If we didn't consider this time dilation effect in our GPS calculations, your navigation would be off track. So, special relativity teaches us that time isn't the same for everything and everywhere. It depends on how things are moving. This concept challenges our thought process about reality. It's like saying our typical comprehension of the universe is a bit off. According to the special theory of relativity, time isn't fixed, it's affected by movement. Some basic ideas like the speed of light always staying the same and how energy and mass are connected have been demonstrated by various experiments, but Brian Cox's groundbreaking idea explained there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory dives deep into the connection between gravity and how the universe is organized. That stirred up the old thought that gravity is merely a force that pulls things from a distance. Rather, it tells us that gravity occurs because objects are bent or curved in spacetime. It's like saying, hey, gravity isn't a mysterious force, it's just how things naturally move in the universe. According to Brian's understanding of general relativity, it means thinking about the universe as a four-dimensional substance combining 3 dimensions of space and 1 of time. In this framework, enormous things like stars, planets, and even U.S. influence how reality is shaped around them. This forms gravity. Imagine space-time like a big stretchy blanket. When something heavy like Earth is placed on it, it makes an imprint in the blanket. If you place something lighter like a ball near the Earth, it will move toward the dead. This is like how objects behave because of gravity, not some baffling force, but rather a response to the bending of space-time. General relativity gives a strong explanation for how things move. In our solar system, for example, planets orbiting the sun can accurately tell us the paths these planets take, including how Earth follows an elliptical path around the sun. According to Brian, this is different from the old thought of gravity simply arranging things, which struggle to explain how planets move as they do. The groundbreaking idea is that space-time is curved like a bendy fabric, which fits better with what we observe. An important moment that demonstrated the correctness of general relativity happened during a solar eclipse in 1919. Sir Arthur Eating led a group to see how light from far away stars bent as it passed near the sun. According to the theory, the sun's mass would make the stereo bend slightly. During the eclipse, the observations matched Einstein's predications, validating the theory. Similarly, as movement can change how we experience time, as indicated by special relativity, gravity also influences time. In places where gravity is especially strong, time moves more slowly in comparison to regions with weaker gravity. So if you were standing near a gigantic object like a black hole, your clock would tick more slowly than one set far away from the strong mass. General relativity introduces the idea of black holes, which are places where gravity is so intense that nothing, not even light, can escape from. At the boundary surrounding a black hole is called the event horizon, and it resembles a final turning point. Once something crosses this threshold, it gets sucked into the black hole with no chance of returning. Einstein's general theory of relativity has huge implications for how the universe is structured. At first, he added something called the cosmological constant to his equations because he thought the universe was static. However, when we found it is expanding, he referred to this as a serious mistake. The idea of an expanding universe based on general relativity is a key part of the Big Bang theory, which explains how the universe started. Another significant concept from general relativity is gravitational waves. These are ripples in the fabric of spacetime caused by extremely massive objects moving quickly, like when black holes or neutron stars collide. In 2015, researchers at the Laser Interferometer Gravitational Wave Observatory LEGO directly detected gravitational waves, providing evidence for another part of Einstein's theory. Over time, researchers have conducted numerous tests to confirm whether general relativity is true, and each time it has proven correct, whether by observing how planets move, the bending of stereo, or the detection of the role of black holes in the flow of time. Gravitational waves general relativity remains a powerful tool for understanding the universe. While saying gravity is clearly FSE may astound us, especially since we all experience gravity every day in the realm of physics, it's not unexpected to explore and investigate different ideas. Research like Brian's often questions established theories, and in the realm of gravity, some challenge the traditional way we ponder this fundamental force. One idea the challenge is trad gravity is called modified Newtonian dynamics, which proposes that gravity acts differently at slow speeds, especially in galaxies, without the need for dark matter. Instead of adding invisible matter, man suggests that gravity strengthens at low speeds. The gravity debate also involves the mysterious concepts of dark matter and dark energy introduced to explain certain anomalies in space. Critics argue that these aren't necessary and that alternative ideas could account for what we observe. Some researchers who disagree with Einstein's gravity theory explore additional possibilities, like theories involving unknown particles or forces that could adjust or improve how we interpret gravity. It's important to emphasize that in science, new ideas are not dismissed, rather they are thoroughly tested to see if they make sense. For example, Einstein's notion of time in four-dimensional space, where time travel may be limited by the speed of light, has been creatively considered alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that traveling back into the past seems unlikely from a physics standpoint. Ongoing experiments and observations aim to determine if these new hypotheses can explain anomalies like the strength of gravity in a way consistent with what we already know. While other ideas have been examined, none have convincingly replaced the well-established rules of gravity. Questioning and testing are indispensable in challenging established ideas. Parts of how science advances lead to further inquiry and a deeper understanding of the universe in the realm of gravity theories. General relativity remains the most important and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena like how planets move and how light bends around massive objects. General relativity remains robust because it is straightforward and accounts for many phenomena as previously discussed. Einstein's special theory of relativity suggests that time can act differently depending on how you're moving. Now let's Investigate how this idea influences real-world situations, particularly in space travel. Space travel is exciting, but it's challenging since space is immense, also is indicated by Einstein's theory. The speed of light is the fastest anything can go. This makes traveling between stars a huge challenge, even with cutting-edge technology, due to the extended time it takes to reach the nearest stars. Consider the famous twin paradox to understand what happens with time when you travel in space. Imagine this one twin stays on Earth, while the other twin goes on a fast journey to a distant star. When the space traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they have effectively traveled into the future. Time is critical for space travelers because the longer the journey, the more time slows down. If space travelers were to visit nearby stars where time slows down significantly, they could age more slowly than people on Earth. While this might seem like a science fiction story, it's a real-world effect from the theory of relativity. Imagine if humans send a team to a star system not too far away. Due to the vast distance, the journey could take many years. Even if they travel fast, for the space travelers on the spaceship, time would feel shorter because of the time dilation effect. However, on Earth, much more time would pass. The stretching of time affects living creatures as well as technology. PCS and communication devices on rockets must account for time dilation for accuracy and proper functioning. Space travel at high speeds presents physical challenge as such as prolonged confinement and exposure to cosmic radiation, as well as the mental impacts of being away from implications for time travel and the universe's fate. Earth for an extended period in our daily lives, we can observe the effects of time dilation. In the global positioning system, GPS relies on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it is crucial to factor in these effects. For accurate GPS calculations failing to do so would significantly impact the accuracy of navigation systems.